Okay, so we're going to talk a little bit more light, and the focus of this video is the creation of light, so how you might produce light, and how you can, like, what it means to have a different amount of energy as far as light goes. Okay, so the first thing we're going to look at is these pictures right here. So I have some pictures, a candle, a whole bunch of, this is kind of like the evolution of cell phones here. There's a rock, this is the sun. This is like this guy, and I put it in because he's holding, like, this is one of the first cell phones, like from back when people used to talk on them. And then here's a little puppy, okay? And all of these things have something in common, and I want you to think about what that might be and let me know. Okay, so the thing that all these things have in common is that they're glowing. They all glow, just like you glow, just like the screen on your computer glows, just like your backpack is glowing right now. Everything is glowing. And the thing is, and I mean, if you could imagine a world where everything was glowing invisible light, it'd be really weird because we're not used to that. Because we can only see things that glow in the spectrum that is visible to us. So like we can see this because it's glowing visible light, just like we can see the sun and other stars. Okay? This rock doesn't look like it's glowing to us. This puppy doesn't look like it. This guy doesn't, but everything is glowing. Okay? And the color that it glows, or the kind of light that it glows, just depends on what temperature it is. Okay? And so we'll talk about that in a second. And then these cell phones, not only are they glowing, but they're producing light another way too. So we'll talk about that as well. So these are producing light because of their temperature, but they have an antenna that they use to produce light as well. And we'll talk about how you might produce light that way. Okay, so this is a curve right here that represents the color of light emitted by an object, okay, based on its temperature. So you have each of these like curves that show the light coming out of something based on its temperature. So if you heat something up to 6,000 Kelvin, it will start to produce visible light and it will look kind of yellowish. Something that has a temperature of 5,000 Kelvin, it's going to be not quite as bright, okay, it won't have the same intensity of light, and it will look more red, okay. Something that's 4,000 kelvins, right over here, it's not quite in the visible light range, so it's going to be glowing mostly in infrared, but it might produce a little bit of visible light at the same time. And as we drop back, you can see that the color of the light produced goes to like lower and lower energy kinds of light. And so eventually things, as they cool down, you can't see them because this curve kind of shifts out of the visible spectrum. Okay? And so you can imagine like something that's room temperature, which is like 400 Kelvin, which is going to be, or like 350 Kelvin. So it's going to be shifted all the way down here. It's still producing light, most likely infrared light, but you can't see that because your eyes can't see that. Okay? And you can take any object and heat it up to 5,000, 6,000 kelvins and make it start producing light. Okay? No matter what it is. Okay? And this is like how light bulbs used to work. Okay? The early light bulbs, or the light, we still use them a little bit. So a light bulb has in it a filament that we run electricity through, and I think it's made of tungsten. And when the current goes through it, it heats up, and it heats up so hot that it gets to this 5,000 to 6,000 Kelvin range and starts producing visible light. But if you have something even this hot, you're going to see that it's producing lots of other kinds of light too. We have all of the light down here and all of the light over here that it's producing as well. So just because we can only see this kind of light doesn't mean it's not also producing those kinds too. And this is why LEDs, which is what we're replacing these tungsten bulbs with, we're replacing with LEDs and fluorescent bulbs. These are much more efficient because instead of glowing to produce all of these kinds of light, it's going to emit just one wavelength of light. And the way that it does that is through a different process instead of getting heated up. Okay, so it's much more efficient because it's just emitting light that we can see instead of all these other kinds of light too. And the last thing I want to mention is that we can actually calculate how much energy a photon has based on its frequency. Okay, so when we talked about mechanical waves, what we learned was that these waves have more energy based on their amplitude. Okay, and this is for a mechanical wave. Alright, but for a light wave, an electromagnetic wave, energy has to do with the frequency. So when you look at the spectrum, the waves with the highest frequency are gamma waves, and the lowest frequency are radio waves. Okay, and so these have the lowest energy, and these have the highest energy, and light is right here in the middle. Okay, and so the light that we can see is kind of in the middle range of energy, and then you have things like X-rays, ultraviolet rays, and these are things that are harmful because can be harmful because of the energy they have. And then things over here are things that are generally safe, so like microwave radiation and infrared. Now, cell phones, TV remotes, Wi-Fi use these kinds of radiation, and then radio is how we communicate, what we use to communicate with cars and stuff. But all those kinds of radiations are safe because of their low levels of energy. Now, in some uses, they can be very powerful. For example, in a microwave oven, it uses microwaves that are all of the same frequency and just uses a whole lot of them. And the frequency of them is really important because the frequency of the radiation in a microwave is designed to trigger water molecules to absorb that energy and increase their temperature. Okay, and so it's basically, microwaves are designed to heat up the water in objects. But I want to talk about real quick how you might create these different kinds of light, or any of these kinds of light, how you might create it. So we saw that you can create light by glowing things, or heating things up and making them glow. And then the other way you can do it is just by accelerating an electron. So if you have an antenna, and if you can cause electrons to accelerate by going one way and then turning around going the other way, these accelerating electrons will produce a photon. Okay, and the quicker they accelerate, the higher the energy because the higher their frequency. Okay, and then we can actually calculate how much energy they have using this formula where this value for H is called Planck's constant. And I'm just going to warn you right now, when you use this in calculations, if you type it in on a calculator on the computer, this number is so small that the computer is going to turn it back into zero probably. Okay, but to wrap this up, I did want to just show you how you might how you can use your calculator to save yourself time when you're doing calculations with scientific notation. And so since this one is so small and I won't be able to use the computer to demonstrate it, I'm going to use a different number. We're going to say 6 times 10 to the negative fifth. I'm just going to show you how to type that in on your calculator real quick. Okay. So depending on the calculator you have, you might have a button that looks like this. Okay. And so that's what we're going to use right now. So 6, and then this button represents times 10 to the power of, and then we type 5, and since it was negative, I'll make it negative. and so I get 0.00006. Okay, so coming back to this, you're going to be using this equation to calculate how much energy light has, or a photon of light has, based on its frequency. Okay, and so when you do so, you're going to be using exponents because this is a really small number. You'll be using scientific notation, and you want to make sure you enter it on your calculator correctly. I'll show you another way you can do it. Let's say that we had light with a frequency of, okay, so let's say I had some light with a frequency of 7 times 10 to the 14th hertz. I wanted to know how much energy it had. Well, I can take this and substitute in there. Let's say that I didn't have my calculator with me, and so I needed to figure out a way to do this simply. Well, when I multiply these, what I can do is simplify the powers of 10. So 10 to the negative 34th and 10 to the 14th, I can combine those. And negative 34 plus 14 would give us 10 to the negative 20th. Okay, and then 6.63 times 7 is going to be about 42. I'll just round it for now. It'll be a little bit bigger because of 0.63. But let's say it was about 42. Or we'll say 45, maybe a little bigger. So 45 times 10 to the negative 20th. And we're almost there, but to fix this, because this is not scientific notation anymore, I have to move the decimal place over 1, making this 4.5 times 10 to the negative 19th. And so that's a way you can do math with scientific notation. If you don't have your calculator available to you, or if you're not sure how to use scientific notation on your calculator.